So let's now look at a specific situation in more details. What we're going to do is look for transverse electric waves in our rectangular waveguide. Okay, so I'm going to do precisely the geometry that we had somewhere here. You see I've got a rectangular cross section here, and what we will do is that we will fix the dimensions here. So we'll say that the dimension here is going to be A, the dimension here is going to be B, okay? And our axes are such that the longest dimension A is in the X direction. So I'll use these conventions in what follows here, okay? So let's just write that down, right? Width A along X, B along Y, and I take A greater than B because that doesn't change anything. It's just a question of choosing our axes properly, okay? Or A greater than or equal, like this. So, because we're doing transverse electric waves, the EZ part of the electric field is going to be 0. Okay, so but we said we had the same equation for BZ, so we're going to need to solve this equation for BZ, okay, in the geometry that we have. Okay, so our fundamental equation is then d2 dx2 plus d2 dy2 plus omega squared over c squared minus k squared, acting on bz of x and y. This must vanish. Okay, so what we're going to do is invoke separation of variables. We're going to choose the form of bz to have a factorized dependence in the two directions. So we will write two functions, big X of little x and big Y of little y, and try to find a solution to this fundamental equation here. Okay, so what do we get? Well, if I just substitute this form for B in this equation here, I just get something that looks like this. So the x derivative only acts on big X, so the y factors out. So I get big Y with now the total derivative, right? Because there's only one dependence here of big X dx squared, plus then the same thing but the other way around, big X with the second y derivative of big Y. Okay, plus then the rest, omega squared over c squared minus k squared, multiplying big X times big Y. This should be equal to 0. Now, the logic of separation of variables says that, you see, if I divide out by x and y, I should get two things that are varying independently of each other and therefore should have some constant relationship to each other. So what that means is that the second derivative of big X with respect to little x, this must be equal to some constant that we'll say is kx squared, okay, times the big X. And the same thing for y, the second derivative of big Y with respect to little y must be equal to another constant, ky squared times big Y. And then it works out if I choose these constants to all add up to being 0. So I get kx squared plus ky squared plus k squared must be equal to omega squared over c squared. So provided I choose my constants like this, fulfilling this constraint, then I will have a solution. Right, so let's just look for the solution for big X. General solution for big X. Well, big X of X has to be a combination of sine and cosines. So I would put some some factor a sine kx times x plus some other amplitude b times the cosine of kx times x. Okay. Now the boundary conditions tell us some things. Okay, so we know that the value of bx must be equal to 0. Okay. So let's see. So we didn't write all the equations here. Maybe I need to write another couple of equations. So you remember here we derived these equations for ex by. You can follow exactly the same logic to derive some equations for bx and by. Okay, so maybe I can just write down these equations as earlier. There was another equation that we could have written for this thing. So the bx that we had was constrained by the following form. In general, square root of c squared minus k squared. Okay, and then there's a k bz dx with a minus omega over c squared times d ez dy. Okay, so that's just another equation that we could have derived before. It's the same derivation as these here. You just substitute e for b essentially and omega for minus omega, and then you get this equation here. Okay, now in this case here, because we're transverse electric, then this electric part is just 0. Okay, and because we only have the field in the z direction, then you see that essentially at the boundary where this field is equal to 0, we also need, because this must vanish, then this one must also vanish at the boundary. Okay. So we also need that the big X with respect to X must be equal to 0, and all of this at X is equal to 0 and X is equal to A, right? So this is just from the requirement that this term also vanishes, and BZ is just big X times big Y. Okay, so that allows us to fix the constants. Okay. I'll write that clearly here. That's a wonderful thus. And thus the big constant that we had, big A, must equal to 0. And we must have that the values of kx, in order for this to work at both places, must be an integer multiple of pi over A. Okay, so it must be pi over A times m, okay, where m is some integer 0, 1, 2, etc. Okay. The same logic applies for a big Y, okay, and you finally get that the bz of x and y has to be some constant, let it be b0, with the cosines of the two allowed wave vectors. So pi mx over a, and then in the y direction it's going to be cosine of pi n y over b. Okay, and this is known as the transverse electric MN mode. Okay, so if you just look again at the constraint that we had on the wave vectors here, I can just re-isolate this wave vector. So it's wave vector is k is just the square root of the difference between omega squared over c squared minus kx squared plus ky squared, but then we can just write this straight out. So there's a pi squared with m over a squared plus n over b squared. Okay, all of this multiplying pi squared, and all of this inside a square root. Okay, so that's a slightly funny thing, because you see, if the frequency that we have here is low enough, then this argument inside the square root can be negative, which means that the wave vector would become imaginary, which means that the wave would be an evanescent wave. It would essentially be exponentially suppressed in z. Okay, so it wouldn't propagate at all. So if omega is less than the critical value defined by these things, so it's less than c times pi times the square root of m over a squared plus n over b squared, which we denote as this omega mn. Okay, and this is called a cutoff frequency. Then there is no wave propagation so z, the dependence, is like e to the minus some modulus of k z. Okay, so this cutoff frequency is really something cool, because you have absolutely no propagation for waves below that. For waves above that, you can get these really nice oscillatory modes that can actually propagate. Okay, so you can just rewrite, kind of handy expression for the propagation wave vector. So rewriting, you can just say that the wave vector is 1 over c with just the square difference between the frequency and the cutoff frequency, okay, and square root of that. Okay. Now the fun thing about these waves is that they have a wave velocity that you can look at, wave velocity. Okay, so this velocity for a wave would just be frequency divided by wave vector, and in our case this is equal to the ratio of the frequency of the cutoff frequency with the frequency squared square root. And the funny thing is that this is then greater than the velocity of light. Okay, so it's just the wave velocity, it's the wavefront velocity. If you look at the group velocity, so V group, that's defined as the differential of the frequency with respect to the wave vector. This is now equal to c times the square root of this combination. And this is okay, it's less than c. Now, if you want the propagation, the physical propagation of physical objects really takes place at the group velocity. You have to think of a wave packet and essentially how you can transmit energy or information there. Actually, I'll leave you with a little exercise. It's exercise 9.30 in the book that actually asks you to show that, for example, energy propagates inside the waveguide at the group velocity, not at the wave velocity, but at the group velocity. Okay, so you can have a look at that. Okay. Now, just as a tiny little add-on, just so you know about them, I just want to spend a couple of minutes on coaxial transmission lines. So what does that look like? Well, you have a cylinder. And inside the cylinder, you have a cable. Okay, so right on the axis of the cylinder here. Okay, so so in that case, you can solve Maxwell's equations quite easily. So this is an actually simpler case. Simpler than the rectangular waveguide, because in this case we can put both the electric and magnetic field components to 0 and still solve Maxwell's equations. So Maxwell's equations, they become really quite simple in this geometry here. Because you can just look at the simple components, cylindrical symmetry like this, lots of components fall away. So for example, Gauss's law would tell you that dEx plus dEy dy, that would be equal to 0. You would look at the z component of curl of E is equal to minus dB dt, and that would tell you that dEy dx minus dEx dy would also be equal to 0. In addition, if you look at the other components, so you just look at the divergence of B is equal to 0, gives you that, and then the Ampere-Maxwell relationship would give you similar equations for the B's here. Okay, and if you look just with a Z dependence here, then again the inhomogeneous Maxwell would give you that C times By is equal to Ex. Okay, and the same thing with the other Z component, telling you CBX is equal to minus EY. And the solution for this is something you've seen before, because it's really just the equations for electrostatics in the absence of matter in a cylindrical geometry. So the solution is just like we had in those cases. We can take the electric field, which is a function of the cylindrical radius with the angle, would just be some number over S with the S hat. Okay, and doing the same thing now for the magnetic sector, it would look just like an infinite straight current. You would have a magnetic field depending on S and phi. That would be A divided by CS with phi hat. Okay, so the actual fields that you have, if you take the just the so these are the E0s, and then if you look at the Z dependence of this, you just reuse the equations that we had before. So the E field that you would get, which is a function of S, phi, Z, and T, this would just be this amplitude A over S with the cosine of some kz minus omega t in the radial direction, and the B would be similarly A over Cs cos of kz minus omega t in the phi direction. Okay, so this is just the electromagnetic content inside a waveguide, and it's kind of nice because I'm sure you've come across these coaxial cables. You've got them in your household, so it's quite nice to be able to solve for the waves in there. Yeah, so you see one simple generalization of this would be, for example, to consider some piece of matter inside the coaxial line, yeah, where you'd need to solve Maxwell's equations now, not in vacuum, but in matter, and then get similar expressions for the electric and the magnetic fields. Okay, but I'll let you study that and prepare for